as we call them. In store 1 uses all 5 brands, store 2 uses all 5 brands, and so forth down the line. So the data is collected in blocks like this. We still have data on each of the 5 treatment levels, brands here in this case, but the data was collected in these blocks. Now, when we have these blocks, we have a different model that describes the data. So if we go back and look at this layout, the layout is supposed to be, here's block 1, K treatment levels, here's block 2, K treatment levels, and so forth. Here's the last block, block N, K different treatment levels there. So we have means across the rows. Notice the dot notation there fits as far as how things are labeled. And we have column means for the different treatment levels and an overall mean there. So we talked about, and I'm just reviewing this a little bit because I have to come back to it again today. We talked about setting up a model for this two-dimensional data, and here's the model equation. Mu is an overall constant. Alpha I is an effect due to rho I, so that's a block effect. Beta J is indexed on J, so it's a column, and so it's a treatment effect. So we call beta J the treatment effect. And then the EIJs are the random noise, the random error in the model. So we define some sums of squares. Total and treatment are the same formulas that we ran into before. Block, same formula that we had before for sum of squares block, and then sum of squares error is just whatever is left over. We could define it that way, but there's officially the formula for it. And this breakdown of sums of squares sum of squares total is the sum of those 3 sums of squares. So we put these in a standard ANOVA table that now looks like this. So in comparison to what we had before, we've got an extra row in this ANOVA table. That's the row dealing with blocks. We have sums of squares, degrees of freedom, mean squares, and 2 F statistics here. One for testing treatment, one for testing blocks. Now, here's where some important ideas come up, again from our model equation. So here, repeated again, is the model equation. Now, what I want to do is to take these y's and average it over I. And I get this thing here, y bar dot j. Now, you're just supposed to be able to look at this and say what the answer is. You don't have to do any calculations or anything. Take this expression that's on the right side of the equation and average it over I. That means sum on I from 1 to n, and then divide by n. Well, mu is a constant in every one of those terms, so I'll just get mu. Alpha I sums to 0 by the sign condition on those parameters. So the alpha i's, when I add on I, drops away. The beta j is a constant with respect to the sum on I, so that's the same in every term of my sum. And so when I take the average, I pop out just the beta j. And then I would get the average of the EIJs, which I would call E bar dot j. And so here's the equation. Now if I look at this thing, on the right side of the equality sign, mu is a constant, beta j is a constant. The E bars are random variables. And they're just simply sample means. So I just quote the standard result for the distribution of a sample mean, and here it is. zero mean variance sigma squared over n. Then down here below, I alternately wrote that information in a different form. The y bar dot j's, those are the averages down the columns, right? They have these, this distribution. Normal with that mean variance sigma squared over n. Then come to the second line up here and do the same sort of thing. But take the yij's and average it over j. So add up j going 1 to k and divide by k. So you look at this, mu is the same in every term, so I get mu. Alpha I is the same in every term. Remember, I'm adding up over j. So I get an alpha I reappearing. The beta j's are going to zero out because the sum on j of the beta j's is 0. So that's the side condition on the beta j's, dropping those out. And then I get an E bar I dot left over on the far right. And again, I claim the distribution of that is just a sample mean, so quote the usual result. But the sample size there is k. Not n. So notice I get a k coming out there. And then I summarize that in this second line here by saying y bar I dot is that normal distribution. The mean is the constant, and then the variance is from the variance of the E bar that we saw above. And the last thing to do is the y bar double dot. So this says I have to add on I and add on j, and then divide by the number of terms in that sum. So if I go up here again to the equation, if I add on I, the alpha i's are 0, add to 0. If I'm adding on j, the beta j's add to 0, so they fall away. The mu is the same in every term, so that remains. And then I get the average of the EIJ's, and so I write this here. So pretty much by the same kind of statements, thinking, argument, I get that y bar double dot has this distribution here. So these are the three distributional results that are going to be helpful for us. Let's turn the page and continue with this story. How am I going to estimate beta j? My prime parameter, actually. That's the jth treatment effect. I look at these distributional results on the bottom of the previous page again, and I can see that I have something here whose expectation is mu plus beta j, but I don't want that mu there. So what I do is look down here to the third line and say, here's something whose expectation is mu. Let's subtract this from this, and then I would have something whose expectation is the beta j. So just looking at these lines tells me automatically what to do. And that's the key to looking at this kind of jump. So that's what it says on the next page here. It says, well, if you take, here it is, if you take the y bar dot j, whose expectation is mu plus beta j, and you subtract from it the y bar double dot, whose expectation is mu, you've got something whose expectation is beta j, what I want. Okay? So, there's the estimate of beta j, the difference of those two means. The jth column mean minus the overall mean. Now, I need to know what kind of distribution this estimate has, because, for example, if I want to form a t-test statistic, I've got to have the denominator. If I want to form a confidence interval, I've got to have the standard error in the plus or minus part. So I need to know what's the variance of this estimate. So now that's got a little trick to it. Here's the answer, which it tells you over here on the right. Well, let's see where that comes from. So I have to write from scratch here again. I'm talking about, let's do the case of just the first one. Y bar dot 1 minus y bar double dot. So this is going to be y bar dot 1 minus y bar dot 1 plus y bar dot 2 plus etc. to the last one. And let's see, this would be y bar dot k. So what I've done there is to take this average of all the data and write it in terms of some components, the average of the first column plus the average of the second column, etc., up to the average of the last column divided by the number of terms in that sum. So this is an alternate way to write the overall average of all the data. Now, the first two pieces combined together, I get 1 minus 1 over k y bar dot 1. And then for all the other ones, I have coefficients of minus 1 over k. These variables, notice, are independent. So what I have is a linear combination of independent random variables. I want to know what's its variance. So our formula from the first day handout, the last page of it actually, says the variance of this linear combination of independent variables is the sum of the variances, making sure that I square the coefficients when I write that out. So the variance of this thing, using that rule, is going to be 1 minus 1 over k squared, sigma squared over n, plus minus 1 over k squared, again another sigma squared over n, and that keeps going, minus 1 over k squared, sigma squared over n, like that. So let's see, you can see I can factor the sigma squared over n out on the one side or the other, say on this side. And what do we have left? 1 minus 1 over k squared, let's write it as k minus 1 over k squared. So I get k minus 1 squared, which is k squared minus 2k plus 1 divided by k squared. And then the next coefficient squared is just simply a 1 over k squared. So are all the rest of them. So I'll just collect them all together and see I have k minus 1 of those. Sorry, I'm writing too far there. Get back up and say that again. So I'm squaring the coefficients in there. Now I'm just doing some algebra. So this thing is k minus 1 over k squared. I square that, it's k minus 1 squared over k squared. Then I get a 1 over k squared. In fact, each of these coefficients is a 1 over k squared. So I collect them all together by saying I have k minus 1 of those 1 over k squares. And so I'm looking at these. I have a common denominator of k squared here, so I can combine those together. And I have k squared, which stands alone, at minus 2k plus 1k. And then I have a plus 1 and a minus 1. So doing a little bit of cancellation there. I have k squared minus k over k squared, which is k minus 1 times k over k squared, which is k minus 1 over k. So that's a simple derivation. It's using some of our basic principles about variance of a linear combination of independent variables and squaring the coefficients, of course, in the formula. And so I'm picking up k minus 1 over k times sigma squared over n. And that's the formula that you see on the handout page here. And so that was a derivation as to where does this come from. Now, I went through all that derivation this time because this kind of thinking, this kind of result comes up 20 more times for us this semester. So you're going to keep seeing it again and again and again. And after a couple times, I'm just going to say to you, do the usual thing. Give me this argument, figure out what the variance formula is going to be. We're going to have to know those variance formulas because they come up in the meat of the statistics. They come up in the confidence interval formulas. They come up in the t-test statistic formulas. So we need to know those variance formulas of various kinds of estimates. So this is the first instance, maybe not the first, but near the first. The second line there says, if we want to estimate the alpha i's, use y bar minus y bar double dot. Now, you can see that happening from the bottom of the previous page. Something that has an alpha I in it is right here, but it's got a mu plus alpha I for its expectation. So I'm going to subtract off the mu, and looking at the last line here, I know how to do that with the y bar double dot. And so I'm going to take this one minus this one, and the expectation should be this minus that, or just alpha I. So same reasoning that we used in the previous case, right? Same reasoning going on here again. So we just apply it one more time. And we get this is the estimate. Now we have to know what's the variance of this estimate. Now, I won't write it down here in front of you today in class, but it's the same proof that we just did. What I'm going to do basically is to say, this is a difference of two things. Now, I can't take the variance of this by just saying, take the sum of the two variances because these two variables are dependent. The y bar I dot is in the y bar double dot somewhere. So that doesn't work. So what I have to do is to write this y bar double dot as a sum of averages and combine them with this one, and then then I get a linear combination of independent variables like we did when we were doing this case, and I work out the same variance with this one. So skipping that derivation, just telling you it's the same as the one we just did. There's the resulting variance formula. The third line here is easy. The estimate of mu is y bar double dot. And its variance is what we had on the bottom of the previous page, sigma squared over kn. So now we know how to estimate the three main parameter types in the problem. The beta j's are the treatment effects, the alpha i's are the block effects, and the beta is the overall effect. So we know how to estimate those, and we have the variance of the estimates there to use as well. Now sometimes we want to make comparisons, and the simplest comparison is a difference. So next it takes up the case of beta j minus beta j prime. How would I estimate that? Well, take a difference between two of these. One with j, the other with j prime. You've got y bar double dot in both of them, so that's going to cancel out. And we're left with just the difference of these two common means as the estimate. So that's how we would simply estimate the difference between two treatment parameters. beta j minus beta j prime. What's the variance of this kind of thing? This is easy. This is the mean of the data in the j's column. This is the mean of the data in the other column. Those are independent. So I have a difference between two independent random variables. The variance of such a difference is simply the sum of the two variances. Now remember, if you like, there's coefficients here. Here the coefficient is plus 1. Here the coefficient is minus 1. And I'm going to be squaring those coefficients. So the 1 squared is 1, the minus 1 squared is again 1, and the variance comes out to be the sum of the two variances. Now this had a variance sigma squared over n. This had a variance of again sigma squared over n. So I add the two together, and I get 2 sigma squared over n. So that's easy, right? There's nothing hard about that. That's sort of a direct result from basic principles. Now, the next line just does the same thing for the alpha parameter. The difference between two alpha parameters is estimated by the difference of two row means. And the variance is the sum of the two variances because they're independent again. And there's the result over there. The last thing here is sometimes we're interested in contrast, something fancier than a simple difference. And so here's a general contrast in the betas with coefficients called C's. To be a contrast, the sum of the C's has to be 0. So what's the estimate of this thing? Well, replace the betas by estimates of them, and you get this. Now, here's your estimate of a single beta j up here. So I'm going to substitute that in for each of the betas in this formula here. Now, you see I'm going to have a minus y bar double dot in every one of those terms. But that's okay because I can kind of factor that out of the sum and then use the fact that the sum of the C's is equal to 0 to say that drops out. So the minus y bar double dots that appear here, when I do the substitution in this line, the y bar double dots are going to drop out because of the condition that the sum of the C's is 0. So I'm left with just this. So this is called psi hat, the estimate for the data of the contrast psi. What's the variance of this kind of thing? Well, looking at this expression, standing back from a little bit and saying, that's a linear combination of independent random variables. Same thought we were using earlier again today. So I square the coefficient times the variance of that. Next one, square the coefficient, variance of the next one. Same pattern going down the line. So the result is, over here, the final variance. I guess I could have written that variance formula in one other way, just the way it would have come out in writing that. It would have been something like this. We would have gotten the sum of the Cj squared times sigma squared over n, like that. Sum on j. Oops, sorry. Sum of the coefficient squared times variance of a variable. And all those variances are the same sigma squared over n. So this is what first, and I just chosen to write it this way for whatever reason, so that sigma squared is just isolated by itself on the field. Okay, well, so then we come to the example 1, which we talked about last time. So if we just quickly review this again, we have the data about the sales of the different brands of the product at the 7 different stores. We calculate by hand the sums of squares, we get the ANOVA table, we do the F-test, we see that just barely we accept H0 on the treatment and we reject H0 on the blocks. So officially we're saying there's no difference due to the brands, and there is a difference due to the stores. Now, I wanted to do some confidence intervals, 95% confidence intervals for pairwise differences beta J minus beta J prime. So I went to this formula for the plus or minus. And you have to flip back a page, and you remember for a difference between 2 betas, this was the variance formula, 2 sigma squared over here. So I pulled that out from the previous page. Here's where I need it. Here's the point from the t-table. Appropriate degrees of freedom coming from the mean square error. There, from the ANOVA table error. And so I pop this all together and I get plus or minus 7. So then I take all the differences between means. Here they are. Here's the number. There's the plus or minus 7.15. And some of those intervals contain 0 and others do not contain 0. So I just indicated what was going on in that regard with the significant label over there. Things are significant if they do not contain 0. So the curious thing that you see happening here is that although for the hypothesis itself, if we do the F-test, the test statistic does not exceed the number from the table, so we accept H0 and say there's no differences due to treatment. When we come down here and look at these pairwise differences, we're saying this one is significantly different from 0, that one is significantly different from 0, and that one is significantly different from 0. So we have an apparent contradiction here, right? And I'll just say, well, that could happen, and we don't worry about that. There's something going on here that we'll have to deal with that's related to the issue of simultaneous inference. This might have an O5 level significance. Each of these confidence intervals, one at a time, might have a 95% confidence rate. Together as a clump, the confidence is not 95%. It's the issue of simultaneous versus individual inference. So anyway, we see this happening, and don't make too big of a deal about it. All right, let's continue on. Here's another example, pine seed data on page 5. So somehow seeds were collected in 4 states, all in the southern part of the country, Louisiana, Texas, Georgia, and Arkansas. And we basically want to know whether these seeds cause trees to grow at the same rate. So what we do is move to Louisiana, and we find 6 blocks of land, and divided them each into 4 plots, and then these plots were planted with the 4 types of seeds. So we're in Louisiana. In some fashion, we have 6 blocks of land. Like that. Each is divided up into 4 parts in some way. So I'm looking at something like that, and I say now for each of these 6 plots of land, I've got 4 subplots in them, and I'm going to choose to plant one of these types of pine seeds in each of those 4 parts. So some of the seeds were originating in Louisiana, others were originating in Texas, others in Georgia, and finally the 4th type of seeds were originating in Arkansas. So, how do we do this? We randomize. We look at any one of these plots of land, and we see there's 4 subplots there, right? Which seed goes in which subplot? We randomize that choice. So we talk about a randomized complete block design. Randomize is right in the title, it's right in the word. There's where it's used. We randomize how the treatments are applied to the blocks. So we've got all that done, and then we wait, it says here 15 years, and we measure the heights of the trees, and we get this data. So here we have, now notice in this example, I've got the blocks on the top and the treatment on the side. So I switch their location, right, from my general layout. But that's artificial. We can have it either way we want, just make sure we keep it straight. So anyway, the blocks are on the top, 6 blocks, and the treatments are on the side. So here's the sums. These aren't the means. I should have put the means here. They're the sums, actually. But there they are. Now, I didn't do the handwork for calculating the sums of squares. I threw this data into Minitab, and Minitab produced this analysis of variance table for me. So notice it labels state, which is the treatment, the state of origin for the seeds. The block is the plot of land, and then error total. So we have the appropriate degrees of freedom. There's the sums of squares, the mean squares, 2F statistics. This one is significant. This one is not significant. So we've identified that there's significant difference due to state of origin, and there's not a significant difference due to the different blocks. Now I'll just write here, there's more that probably should be done, but I won't do it here. The idea would be that, well, testing the H0 is just kind of a big gross statement. Is there a difference or is there not a difference? So we've said there is a difference. If you're going to say there's a difference, it's almost demanded of you to explore what kind of differences are there a little more fully. And so that would be in the more. Perhaps confidence intervals for differences between betas, for example, would be sufficing to do that. Maybe t-tests about that issue could work. We could get into things like Welch t-tests, for example. So all those kinds of things we ran across in the previous handout could come up here in this more. Now, as I said, I'm not going to do any of this more here. I'm just alluding to the fact that more should be done. To do a thorough analysis, we should finish off with more calculations. Okay. So we're trying to culture some kind of bacteria, and there's a nutrient that's of special interest, and wondering how the concentration of this nutrient is affecting the growth of the bacteria. So the data is on the following page. Let's see what it looks like. So what we have to visualize here is that we have 6 blocks. And you can see in the block column, 1, 2, 3, 4, 5, 6. Okay. Within each block is 1, 2, 3, 4, 5 measurements, and they're at a different concentration. So if we look at these concentrations here, there they are. You notice that they're the same in each block. So concentration is the treatment variable. It had said that in the, on the previous page that the value from 1 for concentration was the normal value used. So notice in this experiment how they're positioning each of these levels around 1 so that they're trying to identify which level of concentration is going to give me the highest response. That's what they want to know. And so the levels that they choose are centered around the normal value of 1. So okay, we see that in the data. And then here's the bacteria counts. Now, if you don't like the data laid out this way, this was just convenient for me to print it out this way, you can visualize the data this way. Concentration, 0.6, 0.8, 1, 1.2, 1.4. There's 5 levels of concentration. And then as far as blocks go, 1, 2, 3, 4, 5, 6. So you can imagine this data on bacteria count being written in a 2-dimensional table like this. I just didn't choose to write it that way. I chose to just put it down the columns like this. So there it is. We have some means. There's the means on the response for the different concentration, and here's the means for the response on the different blocks. We notice just in passing that there's quite a difference in the block. Some blocks have very low mean, other blocks have quite high mean. There's quite a difference in the means of the response in different blocks. So we just noticed that in passing. So again, this was done in Minitab. Here's the ANOVA table. If you look at the F-test about concentration, the p-value is 0. We have a very, very significant result there. And for the blocks, the p-value is again 0. So we have a very significant block effect too. So what we say here, just looking at the ANOVA table, is that yes, there's a difference in response due to the concentrations, and there's a difference in the response due to the blocks. Now, the researchers are most interested in the concentration variable, right? What concentration should I use to get the highest response? So if you look back on the previous page, and say, right there. So this would be our result if we use the old concentration of 1. If we would up it to 1.2, we could increase the yield to 182, which is a lot higher. If we go higher than 1.2, it looks like it starts to go back down again. So that would be too high. So the quick, crude answer to my concern would be use 1.2 for the concentration, and that will improve the yield of bacteria. Now, in doing this kind of thinking, what we should perhaps do is to check for statistical significance. We should maybe look at a confidence interval. If I call the parameters on the concentration by betas, we should maybe look at beta 4 minus beta 3 to see whether that amount of difference is statistically significant. I mean, we can see the sample means are definitely different, but they're always going to be different, so that's not really telling us anything. Is that amount of difference statistically significant? Well, a confidence interval on this would help us out.
Could you raise it up a little bit, please? Oh, thanks.
That might work better. So what I'm alluding to here at the end of this example is that the end of the story isn't usually just the ANOVA table. The ANOVA table gives me crude tests of the whole shebang, and that's of interest, yes, but it's not enough detail for an analysis of the data. So we want the ANOVA table to give us some initial crude answers. Is there any differences at all? Yes or no? And then stage 2 would be to explore those differences that might exist in a more careful way. Okay, now that we have the last idea in this handout here, the Latin square design. Those of you on the board remember that you can find that chapter 28 in your textbook is about the Latin square design. So the textbook authors didn't put this topic right following the randomized complete block design. They put it in a different place in the order of things. And I don't agree with the way they put it there. There's a reason for it. Anyway, it's in chapter 28 of the text, and it's pretty much self-contained. You don't have to read chapter 26 and 27 to read chapter 28. So look there for some more information about the Latin square design. Now, what's a Latin square design? Well, it shows you here a simple 4x4 Latin square. So to describe this just quickly, what we have here is 4 letters, A, B, C, D, and we have permutations of them so that each row contains each letter once and only once. Each column contains each letter once and only once. This is called a Latin square. This is an easy one to form because I just started with A, B, C, D, and then slide the letters off to the left. Start with B, C, D, and put A on this end. And slide this row to the left, C, D, A, and then put the D on the end. And finally slide this one to the left, and I get D, A, B, C, like that. So this is a simple way to form a Latin square, although it may not even be the best Latin square to form, but it is one anyway. Each letter will appear once in each row and column. That's what I want. So what I'm having you visualize is that we're going to get data like on the first page of this handout here, two-dimensional data Yij's, but this layout of the data is first of all going to be a square, same number of rows as columns, and secondly, it's going to have a Latin square superimposed on top of the data. So I have these Yij's. So for this kind of data in a Latin square design, size p by p, I'm going to write the data Yijk as mu plus alpha I plus beta j plus gamma k, another parameter, plus Eijk. In the way I'm writing this here, notice the side conditions. The sum of the alphas is 0. The sum of the betas is 0. The sum of the gammas is 0. And the way I'm writing this here is that it's like alpha I is a row effect. Beta j is a column effect. And then gamma k is the treatment effect parameter. So we start with this kind of equation for the data, and then we talk about sums of squares. Sum of squares total. This is the same formula that we've had for sum of squares total in all of our earlier examples. It's basically taking an individual data point, difference to the overall mean, y bar triple dot. Square those differences and add them up. Sum of squares total. Sum of squares R for rows comes out to be this kind of thing. Here's the mean in the ith row, the overall mean. Square those differences, and there's a coefficient here of p. So sum of squares rows follows that kind of a formula, and then it continues on the next page. Further. A sum of squares column, a sum of squares treatment, and finally the remainder is the sum of squares error. We put these in an ANOVA table like this. And 3F statistics now in the ANOVA table. Now before we look at any more detail with this kind of data, let's look at an example of a Latin square. Here it is, example 4 on page 9. So what we're envisioning here are 4 brands of tires labeled A, B, C, and D. We have 4 cars to use for the experiment. The brands of tires are placed on the cars according to a Latin square design. So each car has a wheel position 1, 2, 3, 4. This is maybe right front, left front, right rear, left rear, for example. Position of the wheel on the car. We have 4 different cars, 1, 2, 3, 4. And then we're going to place the different types, different brands of tires on these wheels. So car 1 gets all 4 brands of tires. And which wheel gets which brand of tire is according to this Latin square pattern. C goes on that wheel, B goes on that wheel, A goes on that wheel, D goes on that wheel. If we go to car 2, all 4 brands of tires are again used on car 2 on which wheel? Well, do it this way. R3 uses all 4 brands. R4 uses all 4 brands. And so if you look at the position of the letters in this label here, this is a Latin square design. So if you like, in this example, there's really 2 blocking variables. One is the car, and the other is the wheel position. So here's a set of data which has 2 blocking variables in it. Car and position of the wheel of the car. And then there's a treatment course. Now, this example, I probably should apologize a little bit, because it's a very standard example. I think it's in every book in statistics that I ever encountered. It's very nice that we have 4 wheels on a car. It's very nice that we have 4 brands of tires that we wanted to compare. What if we had 5 brands of tires that we wanted to compare? Now we're stuck because there isn't 5 wheels on a car. So it's kind of contrived a little bit to fit just perfectly the story. But nevertheless, I think it serves to illustrate what's a Latin square design. We have in this layout the actual data, which is the tire wear. There's the mean tire wear for the different wheels. There's some difference there. There's the mean tire wear for the different brands of tires, and then there's more of a difference there even. And so simple summary statistics are given here. So here's the ANOVA table. If you look at the ANOVA table for the quick, crude conclusions, real, not significant. Car, significant difference due to car. Brand, significant difference due to brand. And that's probably the most important conclusion that the researchers would be looking for. They don't really care if there's a difference between the cars. Right? That's not their research goal. But they would care if there's a difference in the wear of the different brands of tires. So again, here I'll write this word one more time. What should you do more exploring differences to see what's going on as far as if there is a significant difference due to the brands, which brands are different from which other brands? Slide back to page 8. I mentioned earlier today that you're going to see this kind of thing happening often. Here it is again. Here's our model equation for the Latin square. The rho variable, column variable, the treatment variable, and the random error term. What kind of distributions do we have with data that follows this kind of a pattern? Well, take the average fixing I. So y bar I dot dot says we're fixing the row at the ith row and averaging over the data. Double dot. Triple subscripts. So again, if we take this equation and we add it over j, this is going to drop out because the sum of the data changes is 0. If we add over k, this drops out because the sum of those on k is 0. And this remains because we're holding subscript I fixed, and that's fixed. So we have those two plus the average of the error terms, which we can write this way. Now we know what this is. This is a sample mean. And And so here's the distribution of sigma b. How many terms are in this average? P. And so we just claim very simply that's the distribution of a sigma b. We put those two pieces of information together in word soup by this first line down here. Y bar I dot dot is normal u plus alpha I sigma squared over p. Now, look at the example again. This is a 4x4 Latin square, right? If I fix a row, it's a real position, and then I average the data, how many terms are in the average? 4. For any row, I average across the data in that row, there's 4 terms in the average. So that's why when I write here, sigma squared over p, because p, the size of the Latin square, is going to be the number of terms in that average. Now the next two lines do the same sort of thinking, but take this and hold j fixed and add the other two subscripts, and then hold k fixed and add on the other two subscripts. We get these kind of lines here, and same normal distribution there on the end coming up one more time. And then the y bar triple dot the average of all the data. Notice how in the variance I've got a p squared coming up in the denominator over here. If you look at the example, and you say, if I take the average of all 16 numbers here, it should be sigma squared over 16. But the 16 is 4 times 4, right? All right, so there it summarizes these distributions at the bottom of the page there for this Latin square design. Now, once we know that, we can figure out, for example, like we did earlier today in the RCV design, we could figure out how to estimate gamma k. That's our treatment effect. Now, this has expectation u plus gamma k, and this has expectation mu. So the difference would cancel out the mu and leave me with gamma k. So the same thinking that we did earlier today just throws it right in front of my face. That's the obvious estimate of the parameter. You're not supposed to think about that very hard at all. It's supposed to be right there in front of your face, knowing these pieces of the formulas that we've been talking about. What's the variance of that kind of thing? Well, there it is. How do I derive this? Go back and do the same derivation we did earlier today. This you write as a sum of these. You actually write this as an average of these. And then you blow it out and realize you have independent pieces. And sum the variances, squaring the coefficients, and you do some algebra, and you end up with that expression. So what I'm alluding to here is that you just repeat again the same argument that I did earlier today. This one here. And this is a good argument to know because it's going to come up a lot. maybe it's even a good possible test question for some new situation. So pay special attention to this. Sometimes students say, well, I don't have to know how to prove anything, I just have to know how to calculate statistics and so forth and so on. But these kind of things could come up as possible test questions. So anyway, that was an important argument that we made there to derive that variance formula. So try it out on this Latin square problem again. And see that you get these results over here for the variances. We want to estimate the difference between two treatment parameters, K and K prime. Take the corresponding difference between sample units. And it's sort of like saying, take this whole thing as an estimate of the first one. And then for the K prime, take that whole thing as an estimate of the second one. And then you'll notice that in there, the line triple dot will be the same in both places and will be canceling out. And you go left for just those difference in sample means. What's the variance of this kind of thing? This is an easy one. Because this is the data in one row. That's up here. This is the data in one K. This is the data in the other K. And those are independent sets of variables. So this mean is independent of that mean. So the variance of this thing is the variance of this plus minus 1 squared drops out. The variance of this, and the sum of the two variances is that. Same thing on this, for contrast, same formula we talked about earlier today, how do you derive the variance of a contrast? So that's just the same thing that we encountered earlier in the handout. So notice how common themes in this data are applying here to the Latin square model as it did to the first model, the randomized complete block model. Details of the formulas change, but the thinking behind what's going on carries over the same. All right. So that's our theory for the Latin square. Let's come to the last page here, where there is a example 5. So the land that we're going to use to plant the wheat has a moisture gradient in one direction due to irrigation and a soil fertility gradient in a perpendicular direction. And so we want to test 5 different seeding rates. The field is set up to a 5x5 Latin square pattern. So the idea would be that we have the field we have 5 different seeding rates. So let's suppose we would make 5 blocks. This is our land. This is the land viewed from a bird's eye. So there's 5 blocks of land. Now there's a moisture gradient on this land, maybe in that direction, where it's moisture on one side and drier on the other side, and so we know that that's going to influence the yield. Now, there's also a fertility gradient in this land. It goes in a reasonably perpendicular direction, maybe like that. And so we imagine the plots of land being divided in that direction into 5 segments. And so we're looking at this 5 by 5 layout of land. There it sits. Now what I want to do is to plant the wheat in those 25 plots of land in sort of a fair, balanced way. And that's what the Latin square does for me. So the Latin square will say each of the seeding rates is going to appear once and only once in each row, and once and only once in each column. That's what I mean by fairly balancing out. So that's what you see in here if you just look at the letters. There's a 5 by 5 Latin square there. So we have on the side row means, we have down below column means, and then the treatment means are down here separate. Here's the ANOVA table. Now the only thing I put in the ANOVA table was this one F statistic because it's the only one I'm interested in. I'm not interested in testing whether there's any difference due to the row variable because I know there is. That's soil fertility or something, right? Is there any difference due to the column variable? Well, I know there is. That's sort of the moisture level. So I don't care about that conclusion. I'm interested in the seeding rates for the wheat, and that's this one row here in the ANOVA table. So the F statistic is 27.7. I don't have it written here on the handout in front of your eye, but I know when you check the F table, you would find that to be significant. So by running this experiment in this Latin square design, we conclude that there is a difference in the yield depending on these seeding rates. Now, we should answer the question, which seeding rates differ from which other seeding rates? How am I going to do that? Well, slide back a page. And say, right here is your story. Analyze the treatment parameter, compare them pairwise like this. So take the difference of the sample means, and then you've got to estimate the plus or minus via this variance formula. Well, you've got almost everything in front of your eye to put that together in just a couple minutes. For instance, going back to the example again. Here's the 5 means. Take the pairwise differences between those 5 means. Then you need the plus or minus. Plus or minus 2 sigma squared over p. Well, p is 5. Okay. And the sigma squared is estimated by the mean square error, which is right there, the 4.7 in this ANOVA table. So right there you've got all the pieces right in front of your eye. If you know what formula you're pulling out to use to write down confidence intervals for all the pairwise differences between treatment effects. So that's what I mean when I said more. There's more to do. It's not hard to do, but you have to follow a certain pattern in doing it. And that's what I hope you're getting out of these different cases that we're looking at. There are common threads to these patterns that keep coming up again and again, and we'll get used to them. Okay, that's enough for today. Let me stop there.